Therefore, if you write a paper, you write a conclusion, there must be an uncertainty associated with it. That's the very nature of scientific work. Okay? I'll come back to you. It's precisely what you talked about on Friday. Yeah, you have a question.
Yeah. Are these table valid only for ideal gas?
That's correct. It's valid only for ideal gas. You go up to 50 atmosphere, 100 atmosphere, all bets are off. Okay. Other questions? All right. If not, let me move on to the next lecture. And I did not know I would be able to go that fast. So I actually did not prepare the PowerPoint, so I have to go through the lecture notes. Apologize. I'm going to have to read it a small print. Again, I don't want to do all the, go through all these things. I just want to point it out what I really think is an important thing in this whole thing. Now, you go back to this table. How many of you have estimated the thermochemical property of a chemical species from scratch? How did you do it?
Statistical mechanics.
I'm sorry?
Statistical mechanics.
Statistical mechanics. Where do you get the energy?
That has to be known somewhere.
Somewhere. Any other? I'm sorry? Quantum chemistry calculation. Group additivity, anyone? Have you all used the codes like a third gas? Automatic mechanism generation codes? Really? Had to be somebody used this stuff here. You did, yeah? Okay. The issue here is that where do you get this thermochemical property? We said that by definition, without the formation is defined as the energy or heat you measure from reacting the elements after a million years at 298 Kelvin, perhaps. You can do this at a high temperature, make things faster. But you have to make sure that you are producing that substance you try to measure. And that's a rather difficult experiment. Where do you get those properties? Okay. And that's the subject that I'm going to talk about next. Doing kinetics, if you want to develop reaction mechanism, my own experience, if you wanted to have a valid reaction model, 60% of effort goes to thermochemistry, 40% of effort goes to kinetics, kinetic rate parameters. Therefore, thermochemical properties are critical to this whole thing. How many of you are chemistry major? Mechanical? Oh, most of them. I have to apologize to the chemists here. I have to talk about something very basic about chemistry. I hope you don't mind. Okay. Let me ask you one question first. Why is the most stable form of carbon in a molecular form has 4 valence structure? Why is the CH4 not a CH3? Now CH2.
Carbon is 4 electrons.
I'm sorry?
Carbon is 2 carbon. It has 4 valence electrons.
SP4.
Okay. First of all, what makes an atom possible? And then we'll go to the molecule. What is an atom? It's a small nucleus, very, very teeny, but occupy a majority of the mass. And you have some electron buzzing around the nucleus, right? So if you look at it from a space standpoint, most of the space is empty. A teeny point with giant space of electrons buzzing around it. Why aren't everything transparent? Well, matters are made of atoms. into a structure. If nucleus or nuclei occupy very small volume, if you squeeze yourself down to angstrom level, you should see everything is empty, right? Except for dots here, dots there. Why aren't things all transparent?
Light interacts with the electron.
I'm sorry?
Because as light's moving through, it's interacting with the electrons.
Ah, because the wavelength of visible light is typically a few hundred nanometer in wavelength. Okay? And therefore, you're probing a matter, our eye sees things is because light bounces off the subject, get into our eyes. Once you get into our eyes, we say, ah, something is there. But our measurement device are photons, and more specifically, photons in visible wavelength range. The result is that matters in principle, even though atoms or structures are made of vastly empty space, where what we are seeing is light scattered from that structure. I won't go into that too much. Why things have a color? You see something that has color is because this thing doesn't absorb that color. Okay? But what matters are made of? Atoms into some sort of structure. Some are crystallized, others are amorphous, but nonetheless, it's because of atoms bonding into each other, into a network. Okay? What happens if the motion of atoms are classical? What shall we see? You look at something, well, this is a blue, this is red, is because that thing does not absorb anything else, absorbs everything else but blue or red. Why wouldn't it absorb blue? After all, absorption is all about a photon hits it in the form of packet of energy. If everything operated classically, wouldn't that energy be absorbed regardless?
There won't be any quantization.
I'm sorry?
There won't be any quantization if it's classical.
There won't be any quantization, so therefore, things have a color. It's purely because energies are quantized. Without quantization, if you just follow Newton mechanics, everything would have been gray. We would live in a gray world. Now, I don't know why it took so long for us to figure that out. Quantum mechanics was the only invention about 80, 90 years ago. I'm sure that if one of you lived 200 years ago, you would have figured that out. Okay. Now, these two things I talked about would have a lot to do with what we're going to discuss for the remaining part of this lecture. But let me do this starting from something Chemistry 101. How many of you know sp3 hybridization? Oh, most of you, so I can skip that part, right? Why things have single bond, double bond? What makes a chemical bond possible? You need 2 electrons to do that. Hey, you say, well, electrons, they ought to repel against each other. What makes them to stay in the vicinity spatially, such that it can lock 2 atoms together, forming a chemical bond? Yes? I'm sorry? It's the spin. Create a magnetic moment. Lock 2 atoms together. It's the 2 little guys, 2 little electrons does that job. Okay? In order to form a chemical bond, you must have 1 electron from the first atom, making itself available. Same for the second. Alrighty. But you know from Pauli's exclusion principle, not every atom buzzing around a nucleus is a covalent or is a valence electron. So if you take a look at a carbon, you look at atomic orbital, the lowest is called the 1s orbital. Each of this represents one electron in opposite spin. Okay. The next is you have 2s orbital. Those are spheres. Spheres within which electron, 2 of them buzzing about. Above that, you have now the p orbital. You have 2px, 2py, and 2pz. Carbon has 6 electrons. Pauli's exclusion principle states you shall start from the lowest energy orbital first. Why? They're further in, closer to the nucleus. And by physics, we know the outer you go, the more energy this electron must have to sustain this motion that spins around the nucleus. You have 1s orbital, you have 2s orbital. Pauli's exclusion principle states you must allow the electrons to occupy the lowest energy orbital first. That in the packing order, 2 going to 1s, 2 going to 2s, you're left with 2. And then this 3 orbital, 2px, 2py, 2pz orbitals are same in energy. Pauli's exclusion principle further states that if you have identical energy orbitals, you shall fill one at a time. Until you fill all of them, you come back, but now by then we run out of electrons in carbon. Now by this picture, the most stable bonding structure of a carbon ought to be CH2. Where does CH4 come from? I remember when I was a high school student, I hated chemistry because you always have to deal with exceptions. I'm too lazy to remember all the rules and exceptions. That turns out for carbon, the exception to Pauli's exclusion principle is that it says when that happens, the 2s and 2p orbitals will start to equalize, forming the sp3 orbital in such a way that all 4 electrons, a hybrid orbital, having 4 identical energy, forming identical energy for the 4 orbitals. And that's how the electron shall fill itself. If it fills itself in this way, then from geometry standpoint, you must have a tetrahedral structure because each of these orbitals is equivalent. And I want to be as further away from each other as possible. Why? Because electrostatic charge repulsion. Alrighty? But these 4 electrons now provide means for you to do bonding, thus methane, in tetrahedral structure CH4. Okay? So starting from that, the very foundation of general inorganic chemistry, or rather general chemistry or Pauli exclusion principle has this exception. It is this exception that dictates all the molecular structure of organic molecules. That also gave rise to the versatility to the carbon. Carbon is in fact is the most versatile element you can ever find on the periodic table. It makes life possible precisely because of that. Well, not only that, you can do sp2 hybridization, you can do sp hybridization. sp2 hybridization led to structure like ethylene, having double carbon-carbon bond. Okay, which by the way, going to sp2 hybridization, I don't want to write it. I noticed that all of you have heard about it. What is the structure of ethylene, C2H4? It's a carbon with a carbon double bond, 2 hydrogen. On each carbon, ethylene is a planar. They lie on the same plane, all 6 atoms. because of sp2 hybridization, you have some pi electrons sticking out, pi electron on the back of the ball. They form interactions above and below the planar structure. And that's what the second bond is. So these two bonds are not equivalent. One is called the sigma bond due to direct overlap of the atomic orbital, leading to spin of two electrons that gives rise to the initial bonding. Then you have electron wave on the top and the bottom overlap each other to form the second bond. Then you have acetylene. C2H2 is linear. You have pi electrons in this direction, you have pi electron in this direction. Okay? And that isn't. Anyhow, so what this is that gave rise to, in sp3 hybridization, that gave rise to the structure of methane, which is tetrahedral. Ethane, you replace one hydrogen atom by another CH3 or called methyl group, and you can add on things to that structure that leading to butane, octane, isooctane, whatnot. You can also cyclize it. I'll jump through all the to form cycloalkane. And in the case of sp2 hybridization, you form aromatics. In the case of aromatics, you take ethylene, three of them form a ring. And each corner is a hydrogen, is a carbon, and has a hydrogen atom bonded to it. It's also planar, except for one thing. In terms of pi electron interactions, they actually do not do it in an alternating fashion. The pi electrons are so close to each other, they actually form a continuous donut on the top of the ring and on the bottom of the ring. That gives rise to stability of aromatics. Okay? And that is an important thing to know for soot formation. And you can write the aromatic ring not like that. The Kikuly structure says that you essentially have equivalent pi electron on the top and on the bottom. So you just write a circle that's acceptable. And you can fuse rings together, this naphthalene, anthraline, phenanthrene, pyrene, and so on. These are what you found in soot, or rather, the large ones of them. Okay? I'll explain at some point how soot forms. All right, oxygen and hydrocarbon, I won't go into too much detail about this. How many of you are working on biofuels? Wow, half of the room. Biofuels are quite many of them are oxygenated. All right, since we're on the subject. And for many of you working on biofuel, let's stay on this topic for 2 minutes. Tell me your opinion about a biofuel. Its future, prospect. And I also want to hear those of you coming from industry. Who wants to start? Okay, nobody wants to talk. So we'll defer this to Friday. Perhaps after hearing, one of you wanted to? After you hear talks from Professor Sokolov, probably you will have strengthened your opinion about the future of biofuel and so on. But I will leave that discussion to Friday. Okay. All right. Skip all this stuff. All right. So what are the differences between gasoline, diesel, and jet fuel? What is the basic difference? Is it because of a chemical difference, property, or physical property? Physical property. Why gasoline typically has 8 carbons on average in terms of molecular weight? Diesel is what, 16, right? And jet fuel is 12. How did we choose that? It all has to do with boiling point. Okay? Gasoline fuel, you're going to have to pre-vaporize it, mix it with oxygen, so you cannot go to very high boiling point. And here you have look at the boiling point as a function of carbon atoms. 8 is somewhere here. It's about 120 degrees C. It shall evaporate. And this is all normal alkane. 120 degrees to pre-vaporize all the fuel is possible. Diesel, you have to burn them in the spray form. Therefore, the boiling point must be higher. You go to about 16. Now you get to about 250 Celsius of boiling point. Jet fuel has somewhere in between. That's about 150 to 200 degrees C boiling point. The other thing that you don't appreciate is that the melting point. Okay? You have a tanker fuel, you don't want it to freeze. So you look at the gasoline fuel, that's 8. Melting point is negative 70, 80 degrees C. That makes sure that if you have a tanker gas, even in the coldest day in Alaska, you'll survive. Well, your car may not, but the gasoline will still be in the liquid form. Okay. So this whole thing has to do with the physical property. All right. And the notes shows you a boiling point fitted as a function of number of carbon for alkenes. As a rule of thumb, not very accurate for boiling points are mostly dependent on molecular weight. Unless you go to aromatics, they will give you very different properties. So let me talk about now where do we get those thermochemical data. Don't read it. I'll get to the point that's important. In early days, before we were able to do quantum chemistry calculation, much of the thermochemical data were derived by empirical rules, known as group additivity theory. Okay. By designing intelligent experiment, you can extract certain thermodynamic properties from, for example, reaction process through the equilibrium constant. Push it back, you get the thermochemical properties. You expand it into a full table. But that's limited to a few chemical compounds. So to expand this list, typically we use group additivity. All right? Today, if you use an automatic mechanism generation code, group additivity is in there somewhere. And that's what gives you the thermochemical properties. Okay? The group additivity theory is pretty simple. Okay. I'll go down to the big molecule. Consider I have a generic organic molecule structure. I have something about aromatics. I have something about alkyl structure. I have something with double bond and triple bond. The group additivity principle states that if you wanted to know or estimate the thermochemical property of this compound, including enthalpy of formation, entropy, and specific heat, what you wanted to know is the contribution of each of this carbon group to the total property you wish to determine. A, B. In terms of contribution, individual contribution of the group themselves, it's not too dependent on the remaining structure of the molecule. That contribution is very localized. The result is, for example, if you're interested in enthalpy or formation contribution of this methyl group, all what you have to know is something about ethane, C2H6. You take the enthalpy of formation of a C2H6 divided by 2. Why? There are 2 methyl groups in it. You get a reasonably good estimate for the contribution from this species, for this group. Whereas the CH2 group looks somewhat like the middle CH2 group in the propene molecule, CH3, CH2, CH3. So now you already have group contribution value for the 2CH3 group. If you know the enthalpy of formation of propene, subtract this 2 methyl group, you get a contribution for the CH2 group, so on and so forth. It's empirical, works greatly. I know that group additivity isn't pretty. Okay? It does not consider higher order coupling effects, that is the interaction among groups. But for its simplicity, it is still very predictive. Today, if you run quantum chemistry code, all right, this whole idea about a quantum chemistry calculation is oversold. All right? No offense to you who do this calculation. Okay, I spent a great amount of time in the 90s. I saw that all the problems can be solved by quantum chemistry, so essentially all my research is about doing that. A little did I know that you cannot solve the Schrödinger equation exactly. You have to approximate it. And that approximation is as dirty as the group additivity theory, take my word. Okay? Now you know the DFT theory, the density functional theory. And that has become the powerhouse of calculations we do. DFT isn't an exact theory. DFT is an approximation. And if you do low-level DFT calculation, like B3 lip, with a small basis set, those of you who did this calculation understand what I mean by that. I may talk about more on Friday. You're going to get answers a lot less accurate than a simple empirical group additivity. In any case, if you do develop a reaction mechanism, the first thing you must do is group additivity. Okay? One of the things that now computer codes are widely available, the Gaussian code, the MoPro for quantum chemistry calculation are so readily available. The tendency is you draw a molecular geometry, dump into your cluster, and get a calculation. That takes about 4 hours if you deal with large enough structure, right? But if you know how to do group additivity, you get an answer for the first estimate. Determine whether this calculation needs to be done or not in 5 minutes. I don't care what. If you wanted to develop reaction models, reaction mechanism, you need to know how to do group additivity. Okay? This is what I call back of envelope calculation. You want to calculate large potential energy surfaces. You need to determine what species you want to consider first. These days I see papers on reaction kinetic potential energy calculation. And it's too big for me, for my taste. Do you know how much 20 kilocalorie per mole of energy difference is in terms of kinetics? A factor of 1,000,000. Okay? So don't underestimate. For those of you who did this type of calculation, you understand what I mean. So that's the principle. And if you were to derive this, don't have to derive this yourself. Codes are widely available from various groups. And much work was done by Joe Bozelli at the NJIT back in the early 90s. And the code somewhere, you type in group additivity, most likely you're going to be able to download the code. And you just feed in how many groups of this I have, how many groups of that I have. And you get a reasonably good estimate for enthalpy of formation and other properties. So does it work? It works quite well for well-defined systems. This is a plot of enthalpy of formation at 298 Kelvin for NL King series of compound. I plotted the enthalpy of formation as a function of the number of carbon atoms. If the group additivity works, stating everything is additive, then this must be a straight line. Because moving one carbon up, you insert one methylene CH2 group into the chain. So each time you add that, it contributes to a certain amount of enthalpy of formation. And if it's additive, it must be linear indeed. Beyond the propane, it is linear. And if you want to stretch it, you go to ethane. That's this dot. It's close enough. Except for methane, it doesn't do a thing. Now, here, that's where the exception is. Okay. You can do the same for entropy. Taking this symmetry number out, I'll talk about later, you also get a more or less a straight line. Oh, sorry, specific heat. You also get a straight line. There's no symmetry number, it's specific heat. Okay? With this principle, if you take the derivative of this curve, if you want to do it acute, the derivative of this line is basically a contribution of CH2 for enthalpy of formation of specific heat. After that, you can tabulate it into something like that. This is the L-King series. And what you can see is experimental value for enthalpy of formation, group additivity prediction for each of the species based on a few data available on the top, and you can see that error predicted by the group additivity is rather good in comparison to the experiment. Same for specific heat and entropy. So for well-defined structure, where the groups have been well-trained, because you have a lot of data available, this is a very good method. As like every empirical method, when you want to extrapolate to conditions under which you don't have many data, or the group is not trained, then you're into trouble. A couple of comments. I'll come back to more to this later. As far as entropy is concerned, you have to worry about the symmetry number. I'll talk more specifically later. This symmetry number is the number of the symmetry of the molecule. In the case of ethane, it's 2. All right, that origin of that again comes from randomness prediction, because if you have an ethane molecule, look like that, spin around, look like that, you won't be able to tell the difference. Therefore, from entropy standpoint, you need to subtract this inference in a quantity of a universal gas constant multiplied by natural log of symmetry number. The origin of that is statistical mechanics. I'll come to that either today or tomorrow. Now, the problem is that like empirical theory, you always have to worry about exceptions. And it's those exceptions that drove me nuts and that drove me to quantum chemistry, only to know there it's as dirty. The different molecular structure, this is cyclohexane, but in cyclohexane you have the boat and the chair structure. Because of a structural difference, those are two different conformers. They would have different impact on enthalpy. And for that matter, also molecular structure difference also leads to entropy and specific heat difference. This is more stable than that. This is the chair, this is the boat. The boat structure is not as stable because these two carbon atoms are too close to each other. They repel each other. Okay, leading to somewhat a high enthalpy of formation. This is type of a correction you have to watch for. Typically, in terms of difference in energy between the two species, around 2 to 3 kilocalories per mole. It's there. It's not that significant. If you want to just do a back of the envelope calculations, good enough not counting them. But if you want to get an accurate value, you have to worry about them. Okay. Move on to the other concept. So these are for stable molecules. What about the radical species? How do you estimate the enthalpy of formation of those species by group additivity? Okay. Where the additive principle lies for radicals? That lies in bound energy. But for that, I need to explain how the potential energy works as a function of separation between two atoms or two moieties of a molecule. All right. What is a chemical bond? A chemical bond forms a covalent bond is because of the spins of the two electrons that hold it together. All right? And if you take a snapshot of an oxygen molecule in this room, it's not like two oxygen atoms, like two balls connected by a rigid rod. It undergoes constant vibration, just like two balls connected by a spring. So if you want to look at the structure of a diatomic molecule, classically, it looks like that. One atom connected by a spring, and this is a spring inside. Okay? the force acting on the spring by Hooke's law is K times X, where X is the displacement from equilibrium. So there is an equilibrium distance between the two atoms. Under which condition? There's no vibration. But if you pull it, let it go. In vacuum, this motion shall go forever. Okay, that's a vibrational motion. What this model essentially says is that if I examine the potential energy with respect to the separation distance of the two atoms, then I have a harmonic oscillator. In other words, as far as potential is concerned, you have this thing that keeps doing back and forth. If I take a derivative of this potential energy with respect to spatial separation, what do I get? Force. Remember, the derivative, spatial derivative of potential energy is force. So when I take a derivative over here, the force acted to repel the two atoms is negative, depending on how you reference this. If I take a derivative here, it's attractive force that grabs the two atoms back. And down below, you take a derivative, the force is equal to 0. That's equilibrium geometry. So if you follow the kinetic energy and the potential energy of the molecule, keep in mind that the total energy is conserved. So kinetic energy must go exactly opposite, such that when you add these two parts together, it's a flat line. Therefore, when you do this harmonic oscillation, when the separation is over here and there's a maximum amplitude of vibration, the velocity would have been 0 over here. Kinetic energy is 0 because the atom, one of the atom, both of them just going to make a turn. If you walk this way, you walk back, there will be one point, a turning point, your velocity is exactly 0, right? So kinetic energy is 0. At which point, your potential energy is the highest. Come back down here and at the bottom, your potential energy is the minimum, your kinetic energy is the highest. Okay? So that's the way how we describe the motion of two atoms as a limiting model. Of course, if you squeeze these two atoms too close to each other, the origin of this part of potential is because electron and electron repulsion. It's because of repulsion, so the potential energy shoots to the roof. It's the same to say that if I take my fist, I cannot push myself into the table. At that point of contact, your potential energy shoots to infinity. Derivative of force is also potential energy, that's the force, is also infinity, right? Okay. So going this part, the potential energies keep going up. Going to that side, as you elongate the chemical bond, eventually, you can pull them so far apart, the two electrons can no longer keep up with the spin about each other. The bond shall break. So realistically, it's not a harmonic oscillator. You pull the two atoms further away, the potential energy has to level off. At infinite separation distance, the two atoms shall not feel each other. There's no attractive force or repulsion force. Therefore, this potential energy should reach some sort of a symptotic value. Okay? That energy at infinite separation relative to the bottom of this potential energy is called the bond energy. You won't understand the 0 point energy yet, and I'll come to that a little later. Zero energy refers to a chemical bond, even at 0 Kelvin, still has evaporation. Okay, I'll come back to that later. For now, all we need to know is the bond dissociation energy is the energy, potential energy at infinite separation minus the potential energy at the bottom of the well. Okay. Turns out, in the context of group additivity theory, for similar chemical bonds, this bound dissociation energy is similar. Okay. Let me give you an example. I don't know if you can see this out from the back, yeah? So this is a table that lists the bound energy of typical carbon-carbon and carbon-hydrogen bond. And this is dissociation energy at 298 Kelvin. So you have two groups in the molecule. That's the bond you're tearing apart between the methyl and the hydrogen. So that's the carbon-hydrogen bond in methane. This is the carbon-hydrogen bond in ethane. The 6 hydrogens are equivalent. Then you have isopropyl with hydrogen. That is the middle carbon atom. You pull the hydrogen out. You ask how much energy do you have to put inside to do that. What you find is that, first of all, to the first order, all of this carbon-hydrogen bond is around 400 to 500 kilojoule per mole. Divided by 4.184. I apologize. Here, everything is in kilojoule. When I move on to next lecture, everything goes to kilocalorie. I know for Europeans, you like to use SI unit, and those are backward. Those are working in the state are still backward. We don't use SI unit, we use calorie. And much of this has to do with how you grew up, how you go through graduate school. Okay? You start thinking a certain unit, you cannot do anything else. But anyhow. So these are typically about 100 kilocalorie per mole to pull a hydrogen atom out. And you go to unsaturated, in some case because of the resonance stabilization. This is a concept I'll talk about perhaps during the week. You're going to get some of the lowered bound energy. Okay, more or less they're around 500. But what's important to recognize here, if I take ethyl with C2H5, methyl with ethyl, methyl with methyl, again, they are around little less than 100 kilocalorie per mole or 400 kilojoule per mole. They're not far apart. The result is that once you tabulate those values, again, based on experimental observation, you can guess for the next molecule which you don't have any measurements in terms of thermochemical property, you can make the chemical similarity rule apply here. Okay? In other words, for ethyl with methyl, this is in propane, pulling a carbon-carbon bond out. It costs you 369 kilojoule per mole of energy. And you go to octane. You pull the methyl group out. It probably costs you the same energy. Through that principle, you can develop the group additivity for radical species, provided you know the properties for the parent molecule. Example, in this case, what you also need to recognize is that the bound energy is basically the enthalpy of reaction. That's the next topic I brought in. Remember I said enthalpy is a potential energy? Bound energy is a potential energy. These two things are equivalent. If you put two atoms out, okay, in a diatomic, into separate fragments, you calculate how much energy you need to do that. That's equivalent to say how much enthalpy do you need to do this. Enthalpy is an energy after all. Okay? So the bound energy and enthalpy are completely equivalent, and enthalpy of reaction in this case for breaking the carbon-carbon bond in ethane is that it's equal to 2 times enthalpy of formation for methyl subtracted by enthalpy of formation of ethane. So if you know something about ethane and you can have a tabulated bound dissociation energy for the carbon-carbon bond, you can determine enthalpy of formation of the methyl radical by that approximation. Are we clear with that? So the early days in the 80s, there a lot of work done on tabulating bound energy, and that had gone out of fashion because of quantum chemistry. Okay. And that is the same principle is used in all group additivity codes. Still, to determine the properties for free radicals. Okay. Skip through that. All right, let's get to the statistical mechanical part of the problem. We have about, 20 minutes here, not much time. Is this class in 12:15 or 12:30? 15? Okay, all right. So I can't complete this. Let me just start this whole thing. We said earlier that things, if we worry about atoms and the molecules, an interaction, the quantum mechanical, energies are in fact quantized. That fact itself gave rise to what we talked about earlier. Things have colors. And the sky is blue. In classical mechanical world, can the sun penetrate the Earth atmosphere? Should all be absorbed by the air. In air, right? The very fact that the sunlight can penetrate Earth's atmosphere is because oxygen, nitrogen, and whatever else in the atmosphere in a visible wavelength range do not absorb the wavelength in 400 to 700 nanometer range. Why? There isn't an energy ladder in a quantized world these molecules can take. If we operate in a classical world, then any quantum energy ought to be able to absorb, can be absorbed by absorbing media, right? We would live in the dark. Again, for that fact, I do not know why it took that long for us to figure it out. Okay. Moving further, there are many, many other examples. Greenhouse effect, global warming, all has to do with quantum mechanics. All right, the greenhouse effect is basic to say our atmosphere is transparent, mostly to visible light, but it's not transparent for carbon dioxide, for infrared, because carbon dioxide and water absorb in an infrared range, leading to capturing of radiation in the night. You should get a steady state so the temperature won't rise, right? So during the day, the sunlight comes, warm up the Earth's surface. In the night, this energy is radiated back out into the space. And this radiation is radiated out in the form of infrared. It turns out this infrared are intercepted by carbon dioxide and water in the ambient air, leading to the greenhouse effect. Greenhouse effect is natural. What will be the temperature of the Earth's surface if there weren't, because we have water and carbon dioxide naturally existing in the atmosphere? Anyone you know? The mean surface temperature would have been 15 degrees C, negative 15 degrees C. The Earth would be a gigantic ice ball. So greenhouse effect isn't bad. It makes life possible, make our life possible. The problem is when you have too much carbon dioxide, infrared absorbing substance, then things go bad. Okay? Something I will talk about perhaps on Wednesday. All this requires to look at this problem somewhat differently. I know that in mechanical engineering discipline, all around the world, we throw away statistical thermodynamics from our undergraduate curriculum. How many of you have taken statistical thermal or mechanics, statistical mechanics in graduate school? Oh, many of you. Good, great. Okay. Now, for those who took it, about half and a half, we can review some of the basic concepts. I won't go to Bose-Einstein stuff, okay? Our goal is talk about some of the things that only of interest to us for combustion. For many of you who hadn't taken statistical mechanics, sit back and just skim the top of what I talk about and go back and find a statistical mechanics course to take. You want to do combustion, you're not credible if you don't understand the statistical mechanics. I mean it. Okay? All right. It all has to do with the fact that energies are quantized. Therefore, the way how we determine thermochemical property must account for this energy quantization. And take one example, specific heat or enthalpy, internal energy. This quantities are all about the molecular motion or atomic motion inside a molecule, right? So if you take an arbitrary molecule with Na number of atoms in that molecule, you ask for the motion of each atom and how many degrees of freedom should you have. An atom can move x, y, and z. So the total degrees of freedom for each molecule is 3 times the number of atoms in the molecule. All right. But for a molecule, you don't want to count things that way, because if an atom moves in that direction by a substantial distance, the rest of atoms has to follow, because after all, they're inside of one molecule. Okay. So the way to do this is not to follow the motion of each atom, but to group this 3 times in 8 degrees of freedom into what you can observe more easily. So that the 3 degrees of freedom due to translation, the whole molecule moves x, y, and z. For a nonlinear molecule, you have 3 rotational degree of freedom. If it's a linear molecule, that's a stick. This spin doesn't count, doesn't provide you any kinetic energy. Only this count, only that count. So you have 2 rotational degree freedom for a linear molecule. Now, you take the difference of a 3Na minus either 6 or 5. That's the remaining degree of freedom doing what? Vibration. So you have 3Na minus 6 vibrational degree of freedom. Again, for nonlinear molecule. And you have 3Na minus 5 for linear molecule. And that concept is pretty easy to understand. Take, for example, the oxygen molecule. Okay. If you look at the oxygen, 3 translation, 2 rotation, 1 vibration. 2 rotation due to the fact that oxygen is diatomic, it should spin around in 2 degrees of freedom. 1 vibration is a simple oscillation. Okay. If you go to a linear polyatomic molecule, what would be an example for a linear polyatomic molecule? 3 atoms. I'm sorry? CO2, okay. Let's do CO2. It has 3 translation, 2 rotation. Because I have 3 atoms, 3 times 3 is 9, minus 5, you have 4 vibrational degree of freedom. So let's account for all 4. You have a carbon, you have an oxygen, and you have another oxygen. It's totally symmetric. You have 4 vibration or more. So the way how we describe this vibration is, this is called, if this is carbon, this is 2 oxygen. This is called a symmetric stretch. The two oxygen atoms doing that. Okay. The second is asymmetric stretch. This. Okay. The third is I'm waving. But there are two ways to wave it. That's degenerate. I can wave this way. I can wave this way. Okay. The next way is rotation. So that's 4 degrees of freedom. Each can be accounted for, can be visualized. Okay. Let's take a look of a triatomic nonlinear molecule. Translation is always 3. In this case, rotation is 3, and vibration is 3. So suddenly, when you don't have this linear molecule now, this is oxygen, this is 2 hydrogen. Okay. One of the vibrational mode, initially doing this is still there. But the one that doing this, where did it go to? Rotation. You lose one vibration, you add that into rotation. Okay. So this is how we classify the motion inside a molecule. And there's a decided advantage in doing that, as I will show. Okay. Now, should I talk about this now? Okay. One of the important issues here is that you can assume that these 3 modes of molecular motion to be decoupled. The resulting model is called the rigid rotor harmonic oscillator assumption. That is, when the molecule is doing rotation, it assumes that the amplitude of vibration is so small, so the moment of inertia in spinning around will never be affected by small amplitude of vibration. As such, they can be decoupled. The same is when you're doing rotation, the centrifugal force shall not elongate the bond. Okay? Those are assumptions. And you can verify how good these assumptions are by assigning, say, well, I have a harmonic oscillator with 2 atoms, and usually that works. I won't go into the detail. It's an assumption, watch out. It's not always right. Okay. Harmonic oscillator also states that the force is essentially described by the Hooke's law. K times delta R, where I replaced X by R, that's the separation. Okay. Such that when you look at the potential energy relative to the equilibrium geometry, you integrate the force to get you as a harmonic oscillator because, what did I do here? The potential is proportional to displacement squared over 2. So if you take a derivative of that, you get that. There's a force constant missing here. Okay. All right. Let's talk about quantum mechanics. Don't be scared. For mechanical engineers, how many of you have taken quantum mechanics? Quantum chemistry? All right. Don't be scared. I can assure you that if you're a mechanical engineer, you won't get lost in this whole quantum world. Okay. The whole thing about quantum mechanics is the particle-wave duality argument. Now, Newton time is about particles. Everything comes as a particle. Photons are particles. And then you have the theory of a wave. Much of the debate in the 20th century, 19th century was about photons, small things, light things. Are they wave or are they particle? It turns out that various experiments essentially shows they have this duality. It's neither particle nor wave. They're probably both. And you remember this classical experiment. You take an electron beam, you realize an electron can simultaneously pass through 2 small slits, right? Leading to a diffraction pattern behind. So if it's a particle, this photon ought to go through one but not the other. So there must be some wave. characteristics. It's a particle, but because all of these things has, except for photon, all has certain mass. Electron has its own mass. Everything has a mass, must be a particle. Okay? It is that duality that led to development of quantum mechanics and came with Heisenberg's uncertainty principle. Many science principles, famous ones, are those who tell you what cannot be done. Don't feel bad. What a Heisenberg uncertainty principle basically says that it's not possible to specify the momentum and coordinate of a particle simultaneously. If you know its momentum, you won't know its position. If you know its position, you won't know its momentum. Why is it? You see an airplane flying. You say, here's an airplane. That's its spatial position. And I measure next one position. If I clock it, I get its speed. I get its velocity. If I know the mass of this airplane, I know the momentum. So I know the position and the momentum by doing this measurement. Why can't I do this for an electron?
The very act of measuring it,
I'm sorry?
the very act of measuring it moves its position.
I'm sorry?
The making the measurement itself changes its.
That's right. Remember, all measurement has to be done by a media of another particle. We measure something by our eyes, by sound. It's all because something bounced off something, hit our sensory devices, our eye, our ears. A photon bounced off that wall coming into my eyes. I know the wall is there, perhaps about 10 meters away from me, and the wall is not moving. Implicitly, what I'm doing there is I take a time delta t and I say, well, spatial position of that wall, did it change? No, then momentum is 0. What if that photon hit that wall and actually knocked that wall 10 meters away? Well, that would happen. If an electron is your measurement device, electron bumping into another electron would fundamentally change the position of that electron, right? And if it does, it must change its momentum too. So that's the reason why you can't determine the momentum and the coordinate of a particle at small scale all at the same time. Again, something obvious. You lived 200 years ago, you realize this whole thing, you would have invented the Heisenberg uncertainty principle. The point is the consequence of it. That messed up the whole thing. Newton mechanics is great. Newton mechanics gave us a lot of ego. Imagine, all this Newton mechanic theory is if we know initial position and velocity of every atom, every molecule, every dust, every planet, every star, we shall be able to predict the future. All you have to do is map out spatial position and momentum of everything you can see. Quantum mechanics says, you can do this for a star. You can't do this for anything that's small. So that's a big blow to our ego, that science isn't going to be able to predict everything, and we live the consequence and suffering the consequence since then. But this is not to say we cannot make prediction about small things, except we have to go to quantum mechanics that describes an entity at a small scale by a wave function, or the postulate of wave function. That's the sum. It's expressed as a function of some spatial distance evolving over time. All the way, what do we know is that this is a probability density function. And if you sum all this, look at the total probability, there must be unity, integrate everything together. Okay? In the phase space, in the coordinate, and so on and so forth. So that must be normalized to work. So then the next step is just like every other law, you fudge it. How many of you have done exam? You ask the proof from point A to point B. You're stuck from point A, you go prove backwards. And sometimes it works. It usually works better. You didn't do anything wrong. That's how we do science. That time you had some information about the wave function of a hydrogen atom. Again, it's postulated. It's simple. It has one electron buzzing about. Okay? And you basically devise an equation that will give that exactly that solution. And you verify the solution of this equation for some bigger system. And for things that we deal with, chemical reactions, this equation hasn't failed. This equation for sure is incorrect, but hasn't failed. We'll live with that. It's the Schrodinger equation. Okay. And I have 1 minute left. Let me just describe this. It's not a 100% fudge. It's a disrespect to Schrodinger if I say it's a 100% fudge. Its origin of that is that you have a potential energy term, you have a kinetic energy term. You sum together, on the right-hand side is basically total energy. It is still based on construction of classical mechanics, rooted deeply in thermodynamics, except for it's expressed in this form. Now, let's quit today. I will come back to start from the Schrodinger equation, and we'll solve a couple of small problems to illustrate the translational motion, the rotational motion, and the vibrational motion. Once we learn how energies are quantized, then we may be able to determine the specific heat, the enthalpy, through something called a partition function. Okay?